Find an expression for the electric potential at the point P. P is located on the central axis of a uniform charged ring of radius A and total charge Q. You know we have ring one-dimensional object. For the total ring Q equals to lambda times L total. L is the total length of the ring. You know the total length of the ring equals to 2 pi r. Okay, if we have only L with angle theta, here we have L and R, we can say L equals to R times theta. If we have a total ring, in this case, theta equals to 2 pi. Okay, so L equals to R times 2 pi. This is the total Q. Q equals to L times R times 2 pi. And dq for a small portion here, dq equals to L dl, lambda dl. Okay, in this case, you can say also for a small dl, let's say here we have dl, and here we have d theta with a radius r. dl equals to r d theta. Okay, so this is the value of q and dq. Now, you know, I take a small element of the ring with dq as charge and with dl length dl. dq will create at the point P an electric potential dV. Okay, so dV is it's the electric potential by dq. We can calculate dV equals to k dq divided by the distance between dq and the point equals to r. And here we have this right triangle, r equals to radical x squared plus a squared. You know, in general, we cannot calculate the electric potential at only one point. To calculate V at the point P, we have to take 2 points, okay? And we do the integral between them. Here, we have to choose a known value of electric potential. We take this value at infinity. You know, at infinity, V at infinity equals to O. Okay, so we can take V between infinity and P. In this case, we can say V between infinity and P and the distance between infinity and P. So here we have Vp minus V infinity equals to K is constant. You know here about radical x squared plus a squared. If we move dq on the ring, x is constant, x will be constant, a is constant, so radical x squared plus a squared is constant. So we can get out this value. So finally, we have k divided by radical x squared plus a squared, and dq equals to lambda dl. Lambda is constant, we get the integral of dl. You know the integral of dl, dl will be between 0 and L. Okay, here we have this point between 0 and the total length of the ring. So between 0 and L. So we can say Vp minus V infinity equals to K lambda times L divided by x square plus a square. You know L equals to 2 pi times R, the perimeter of the ring. So we can say K lambda times 2 pi R 2 pi A. Here R equals to A. Divided by x square plus a square. Here we can put, V infinity equals to 0. So finally we can write Vp equals to, you can put K equals to 1 divided by 4 pi epsilon 0. So we have 4 pi epsilon 0 radical x square plus a square, and here we have 2 pi lambda a. Okay, here maybe I can ask you to find the expression in function of q. Okay, it's easy. You can say total q equals to lambda times L. So lambda equals to here equals to q divided by L. L equals to 2 pi a. Okay, so here we can write lambda. We can put lambda equals to q times q divided by 2 pi a. 2 pi a and 2 pi a, we get finally Vp equals to q divided by 4 pi epsilon 0 radical x square plus a square. Listen, this one is Vp in terms of q, and this one is Vp in terms of lambda. Okay, it depends the problem. You can use this one or this one as you like. Find an expression for the electric potential at the point P. So first of all, we have to find V at the point P. You know P is located on the x-axis, passing through the center of a ring. This ring is uniformly charged. It means lambda is constant. When we have a uniform charged ring, we have a constant lambda. We have a ring, it means we have a one-dimensional object. In this case, we have Q total equals to lambda times L total. L is the length of the perimeter of the ring. You know, if we have L and with angle theta and radius r, you can say L equals to r times theta. In the case of ring, we have theta equals to 2 pi. So L total equals to r times 2 pi. In this case, we have r equals to a, so we can write q equals to lambda times 2 pi a. If we have small dq, equals to lambda times dl. dl equals to r d theta. Okay, we can say this one lambda l, and this one we have lambda times r d theta or l d theta. Anyway, now I want to calculate the total electric potential created by this ring at the point P. You know, in general, we have to take a small element of the ring with length dl. Here is dl with dq. dq will create at the point P. So we can say here dq creates at the point P an electric potential dv. Okay, so we can say dv equals to k dq divided by the distance between dq and the point P. With this right triangle, we get r equals to integral x squared plus a squared. Okay, we calculate the integral. You know, the integral of dv, we have v. Anyway, if you want to calculate v at a point, you have to find the limit or the difference of the electric potential. We can take a known value of electric potential at infinity. We can take a point at infinity, and you know v infinity equals to O, and the point P. So we have between infinity and the point P. So we have Vp minus V infinity, okay, equals to K is constant. Inside we have dq equals to R A. We have lambda R d theta. We can say, okay, we can put dq anyway. We can write dq. Here, if we turn dq around the circle, x will be constant, and also the distance is constant, okay, because the distance will be from this point to here. It's constant at any position. If we turn like this, r is constant. So this value is constant. We can put it outside the integral. We can write finally, we have k divided by x squared plus a squared integral dq. And you know the integral of dq equals to q. Here we get kq divided by x squared plus a squared. This is the value of v at the point P. Okay, you know v infinity equals to O. Vp. This is part A. Part B, I have to find the expression of the magnitude of the electric field at the point P. We have to find E at the point P. Okay, you know, to calculate, you have a relation between the electric potential and the field. Here, you know, dV equals to minus E dot dr. Okay, so we can say E equals to minus dV divided by dr. Let's take the magnitude, okay? The magnitude. And here we are along x-axis. So dr, here we have x-axis. So dr is dx. We can say dx equals to minus d divided by dx, the derivative of v equals to kq divided by x square plus a square half. Okay. Equals to, k is constant, q is constant. We can put it out, minus kq times d divided by dx. We can put this value here. We get x square plus a square minus half. We have to calculate the derivative of x square plus a square power minus half. It's equal to minus k q times minus half x square plus a square minus half minus 1 times 2x. So finally we have e equals to minus kq. Here we have minus, we can put plus, okay, divided by 2. Okay, here we have 2 and 2, so we don't have here 2. We have x divided by minus half minus 1. We can put here x square plus a square. We put it 3 over 2. This is the electric field created at the point P. So it's easy to calculate the electric field from the electric potential. Okay. In the next video, I want to calculate the total electric potential created at the point P by a cylinder. Okay. Like this. So see you in the next video.